Hello, my name is Syed Farrukh. I'm a student at Wayne State University. My major is electrical engineering. So today my topic for informative summary presentation is driverless car change lanes more like human do. So driver cars change lanes like human do. What is the main motive behind it? So there are computer algorithms that make car changing lanes autonomously possible. So these algorithms use the feedback from our lane detection sensors and the cameras that are embedded in the cars. And then today's modern cars, they have a lot of sensors. I have, so they change lanes easily with using the feedback from the sensors. Moreover, if we move forward, what is the purpose of that article? So what the article proposes is to identify the minimum amount of information needed for vehicles to replicate human-like behavior while changing lanes. What would you make out of it is to let the system, the computer system, know what sort of information, what minimum information we need to exactly, not just exactly, but to match the human driver performance when we change the lanes uh, driving, and we want this to be done autonomously without any human effort. So what minimum information we need, because when you're driving on a road, there's so many information going on. There's so many cars going on, and they're having a different speeds. One car is driving at 50, other is driving at 60. You do not know how to negotiate between those two. Like, we know how to do it if we find enough space, but how the computer does that, we want to tell that. So what a uh, successful system would be like is if it maintains a balanced combination of conservative and aggression when changing lanes and autonomously. Like, it maintains the safety, and also at the same time it be smart. So if it finds a space beside it, it can change the lane instantly. Moving forward, there are existing algorithms, but there are some issues with it also at the same time. And the main issue with the existing algorithm is that it relies heavily on the detailed statistical model of driving conditions. That means it needs to know everything that's on the roadmap, all the vehicles, all their speeds, how they're operating, how they are not operating, what are the weather conditions. This is completely impractical. Like, a computer system cannot know it in real time, all those conditions, all the vehicles, what are the driving speeds, and what are the directions are. You cannot, even as humans, you cannot know this, right? You drive on your own instincts, you trust your instincts, you trust your driving skills, but a computer, you cannot teach that. So, and some algorithms are so conservative that they never change lanes. They play safe. They're like, okay, we're not going to change a lane if we find any car. So that is a very impractical algorithm, and it's not practical. So we want something better. How can we make it better? There's a possible solution proposed in the article. And the possible solution is we need to find a buffer zone, that is a safety net, you would say, in a more simplistic term, a safety net, like a safety net of distance maintained within the vehicle or cars, I would say, within the cars, within two different cars. If you have that safety net maintained, the vehicles can change the lanes if that distance is, if it's away from that safety net. So the buffer zone should include the current position of the car and also the future estimated position of vehicle with some time frame, by knowing when the vehicle, after 5 seconds, where our car is going to be on the road. If we are driving with a 50-mile speed, it will just calculate the time and the distance, the time and speed, and will tell us what distance we would be in. So this way, if the car maintains a buffered zone value, it would have a very good safety zone, and it would not crash into other cars. So, but there's a buffer zone dilemma also, and the dilemma is if the car on the road are fast moving and the traffic is very dense, then those buffer zone values, the pre-program that we put into our computers, into the computer of the cars, are not going to change, and the car is going to play according to the rules of the provided buffer zone values, and this way it will not even change a lane, and this would be a very impractical, because we want, when moving on a fast lane, we want to be like we human drivers do. We change lanes, right? We zip through the traffic. If there's a space, we change the lane, and then we change the lane right to left, to make sure we are not stuck in a single lane, so that we can save our time. So that's a dilemma. How can we solve this dilemma? Well, the MIT research proposed that if the buffer zone values are performing worse than a human driver would do, then it has to change. It has to recalculate the buffer zone values, given the driving conditions on a freeway. So it has to recalculate those buffer zone values. It cannot operate with the same buffer zone values. So the new buffer zone values are calculated using a Gaussian distribution and logistic function. We multiply those values. The Gaussian distribution is used for probability and statistics. So those statistic values, when we recalculate them, we get the new buffer zone values, and that would make our cars more efficient and more agile while driving autonomously. That's the main focus. So in conclusion, the algorithms that MIT research proposed turned out to be a success story, and they tested it using 16 vehicles on a freeway, on a simulation basically. They tested it, and all the vehicles performed within their buffer zone values, and there was no collision noted, and they all performed safely while being smart at the same time. So this new technology, the autonomous driving, is still a challenge, specifically lane changing, because we have to know what others going to do at the same time. And more extensive research are also taking place for autonomous driving. So thank you very much. I hope you have a good day. This is my presentation.